So, maybe on that note, probability. So how many of you, so what are statistics and probabilities? Anybody want to hazard a definition of one or the other? And there's a closely related word that we frequently use in our sciences called metrics, which is like a particularly bureaucratic version. I don't really know what the difference between a metric and a statistic is, I guess, but likelihood of something occurring. Okay, good. So that's a first point. We're gonna get specific about how we might estimate probabilities and even what it means that something might be probabilistic in a minute. So what's a statistic then? So this is sort of an interesting transition because in class so far, and even when we got to the section on dynamical systems and chaos, we started to talk about how things might go kind of haywire. We've always had the sense that our variables were deterministic. So deterministic means there is just one answer to the question you are asking. Like you take an equation, you solve it, there's a solution. But how does the concept of chaos kind of mess with that conception of the world? We talked a little bit about neighboring initial conditions in chaos diverging from each other. You know, like we showed the picture of the Newton's method solver that had the fractals in it, and we said, you know, the basins of attraction get like crazy. So if you're just a little bit different, you would converge to a different steady state solution. So that is the fundamental principle of chaos, is that very close neighbors might have qualitatively different behavior after some chaotic. So that leads to a sense of maybe, what if you don't measure that point at infinite precision, but you measure it at finite precision? So in the beginning of the class, we talked a lot about precision of things like regarding Taylor series or truncated Fourier series, where we said, oh, you know, this is probably good enough for whatever. So now we want to come back to that, but with a concept that the world is partly chaotic. A lot of the systems we've talked about, all the continuum mechanics equations we had, have chaos in them under certain conditions. But also that what other kinds of uncertainty might we have that were kind of irreducible? Maybe get a little better at them, but fundamentally irreducible. Like, what are some of the other things that you might do if you were taking an experiment or simulating something in a computer, I guess?
If you're doing an experiment, there's precision of your equipment.
Yeah, so you take a measurement that's going to have some limited precision, some limited accuracy. So we have a sense that and even if you repeat the same experiment over and over again, you're going to get slightly different answers because of the instrumental precision. So that's part of the game. So does everybody know the difference between precision and accuracy? So precision is how many digits you get, but accuracy is how close to the true answer it is. So they're slightly different. We'll talk a little bit about the standard deviation and the mean of statistical, which is kind of like something that gets the mean right and is accurate. Something that has a small standard deviation is precise. So there are statistical concepts to that. And in a computer, like we put a number in the computer, it has limited precision. Like it doesn't have an infinite number of digits. So it's not a root. If you try and represent pi in the computer, it's only how many digits it is. Something that has an infinite amount of precision required to conceptualize it isn't necessarily rendered that way in the computer. So in both cases, we have kind of a finite precision. So probability and statistics is an approach to just that whole conceptual framing that the world has randomness and imprecision in it. And rather than trying to eliminate that, what you do in statistics and probability is you try and estimate those levels of precision. So rather than thinking of deterministic systems, we think of systems that are random, that variables are random, but random doesn't mean totally random, it means well-constrained randomness. So what we're going to try and think about is how to estimate the randomness in a variable in a set of measurements, or even how to kind of use the language of probability to try and describe the level of randomness in something. And this, I think, is one of the things that students in DEEPS always ask for more of, because like it's frequently the case that you'll be writing a paper or something like that, and you won't really know how to get at the level of precision. And so for the remainder of the semester, we're basically going to work on ways to try and think about how to get more precise in how you describe it, how you do things like propagate error through from the beginning of one equation with random variables to an answer, how much randomness is retained by that answer, and how do we think about that, how do we put those pieces together. So we're going to use both the kind of traditional way of doing that, which is like pencil and paper stuff, and we'll talk about how to do that, but we're also going to talk about how to estimate things using MATLAB, which they're almost cheating because they work so well with so little effort that if you have a computer and you can calculate 10,000 samples out of a set of data, you actually can do a pretty decent job of estimating these pieces in kind of an automated way. So we're going to build toward that. And the homework will have a little bit of computer stuff, which we talked about last time because of that. So does everybody have MATLAB installed on their computer? Okay, you should install it. It's free. You have to go to software.brown.edu and then you can
have to use MATLAB?
It will be significantly easier if you do. I'll put it that way. You can use R or something else, but I have code in MATLAB, so the homework will just give you code, and you can just type the button and it'll go. Type the command and it'll work.
There's no web browser for MATLAB if you don't want to.
Yeah. Python is also a good alternative, but unfortunately, I just haven't written the exercise in Python yet. But so rather than having multiple flavors, it's easy.
Upstairs also have MATLAB.
And you can also do it in the lab upstairs.
Okay.
Computers upstairs. Yeah. Okay. So that's part of the game. Okay. So, probability, and metrics. We didn't say what a metric is. A metric is just a measure of something. So it might be like the average temperature in a region, or it might be like the consumer price index is a metric, which is a really weird one. But it kind of reflects inflation. It's like a weird derived quantity that has lots of different pieces going into it. So a metric would have statistics. You take the mean of a metric, you take the standard deviation of a metric, and it would also have some sense of the probability that underlies it. So we'd like to start to think about that. So I like thinking about probabilities with two different visualizations. The first is a histogram, and the second is a Venn diagram. I suspect everybody in here has seen those, but let's talk about them in a way that makes it transition into where the equations come from, sort of natural. Okay? So, does everybody know what a histogram is? A histogram is like an estimate of probabilities. So let's make a histogram. Okay. Apples, pears, oranges. Okay, this is a histogram of fruit. And on this axis, the important thing in a histogram is that this axis measures the number of occurrences. So we're gonna imagine, like, if you imagine you got a bag of fruit that you just bought at the grocery store, and it's filled with apples, pears, and oranges. You reach into the bag, you don't look, and you take one out, and it might be a pear. And then you do it again, and it might be an apple. Then you get 2 oranges, and another pear, and another orange, another pear, whatever. Something like that. That's 4, that's 8. Very good. So if I don't do it right, then the ratios get complicated. Actually, let's do 2 more. Okay. So, all I did was, as the data came in, I categorized it into bins. The bins don't need a number to be a histogram. They could just be categories like this. Does that make sense to everybody? So the histogram is the count of the number of occurrences of each category. So what is the likelihood of getting an apple based on this collected data? 1 in 10. And you got that by just saying how many were in this category divided by the total number. So we could say that the histogram of the ice category is just the number of occurrences and the probability associated with that is the histogram value divided by the total number. Okay. So what if we assign a dollar value to each of these? We could say, suppose an apple costs $1, a pear costs $2, and an orange costs $3. Does that make sense to everybody? So the only thing I've done now is I've assigned an ordinate, a numbered set of categories together with the histogram. So what now is the likelihood that I draw a $2 piece of fruit out of my bag? %, so 3 out of 10. So now I might think of probability as being a function of the cost. So this is the cost in bin 1, this is the cost in bin 2, this is the cost in bin 3. So I can start talking about the probability of a number. And that would be the number of occurrences times the value of that occurrence over the total would be, oh, sorry. No, that's still this. That's the probability, which is still the same as the probability before, but now we've got 2 different labels. One of them is numeric, and one of them is just by category. So what is the average cost of the fruit? $2 if each of these categories had the same likelihood, but they don't have the same likelihood, right? So how do I form the average if I didn't even know about this? How would I form the average? What would be my average cost? I could say I take all of the costs for, I'm going to use a different symbol. And how many? I have 10 fruits. So I could sum from j equals 1 to 10, and then I divide by 10, and that would be my average cost. So here I'm using this angle bracket to mean the expectation value or average. We're going to use that in a lot of different ways, but that's just notation. And then here's our normal sum. And so I did the sum. I guess I could use n, which was the total number over here, and I did the total number here. So how many times do I have to do this? I have to do this 10 times, right? I guess I'm going all the way up to big N. If I want to have more than 10, I can do that. So bing, 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 bing. But look, this is similar to this. It has a big N in the downstairs. But what's different about I and J? How many J's did I do, and how many categories are there? There are 10 J's, and there are only 3 I's. But I could have just as well said that the average cost was the sum as I goes from 1 to 3. So the number of categories, not the total number, of the histogram of I times the cost of I divided by the total number. Everybody see what I mean? This is just the same. I'm just bidding them up. So instead of going all the way to n, I'm only going to do 3, which I could write instead as the sum over the probability of I times the cost of I, and I equals 1 to 3. So, everybody see what happened here? So the probability here is appearing now as a weighting factor for the different categories in order to convert from the category specific value to the expectation value over the whole bunch. That make sense to everybody? We've actually already seen this before when we talked about doing an average over a volume, where we said take the variable and multiply it by some weighting function, integrate over all possible values, and that divided by the integral of the weighting function would be equal to the expectation value of that variable. Right? So in this case, this weighting function, this is the sum version, this has a discrete set of things. This is a continuous version. And the discrete set of things we're just summing up. We didn't have to do this bottom part. Why didn't we have to do the bottom part? Up here?
Because it's 1.
Because it's 1 because we've already divided by the total number of things. So the probability, the histogram divided by the total number of things that went into the histogram is already factored out. Or another way to put it is the sum of the probabilities over the 3 categories is already 1. Right? So we have, implicit in this, we know that the sum, I equals 1 to 3, P of xi equals 1. That's what we meant by the weighting. We could have had a hidden 4th category that we didn't know about that was maybe doing something that we weren't paying attention to at all. So this is an implicit statement about we have sampled all of the possibilities. And there's also something, interpreting this as the probability means something about each of these x's. So the probability of getting an apple or a pear and orange are not the same. But the original, each of these x's has equal probability. So each of these is a repeated experiment drawing from the same set of likelihoods. Does that make sense? So in order to build a histogram, we have to do an experiment, and each set of the experiments, we're not expecting things to be changing from time to time. The histogram, each experiment is like another repeated experiment. They're all the same, they're all interchangeable. The outcomes may have unequal weights, but each of these is equally likely in there. Does that make sense to everybody? So it's important to know that the first step is we have something that we expect to be uniformly distributed, equal likelihood on every event. It is then repeating those equal likelihood experiments, they're all the same, and taking some outcome from all of them and measuring the likelihood of the different outcomes that we build our system, our histogram. Does that make sense, everybody? Okay, so what is our average? So we have one. Is it easier to calculate it this way or easier to calculate it this way?
Second way.
What? Second way is easier because there's only 3 things, right? So I have 1/10 times $1, so $1 times 1/10 plus $2 times 3/10, 3/10 plus $3 times 6/10, $3 times 6/10, which is 0.1 plus 0.6 plus 1.8. Did I do that right? That's 0.6 plus 1.8, 1.19, 2.5. Did I do that right? Yeah, all right. So $2.5 is our average. So it's a little higher than $2. And that's exactly the point of when Samantha said $2, it's $2 if they were equally likely, but because they're not equally likely, it's a little more than $2. So how much money did we spend buying all these? $25. 10 of them, each average cost $2. Right? Does that make sense? Or I could have done it, that's essentially going backwards instead of this one. I could have said I spent $25 total, which is just summing up 1 plus 2 plus 2 plus 2 plus 3 plus 2 up to 25 and divided by 10 pieces of fruit. Okay? Is this the only way I could have spent $25 on 10 pieces of fruit? Definitely not, right? Like I could have shuffled them around some. What's another statistic that would help describe the distribution among these? So this is the mean. What else might we like to think about?
What is that?
Something like the shape?
The bell thing.
The bell thing, exactly. So we're heading towards probability distributions. So if I did this an infinite number of times, I might actually make a function out of this, say that I really knew it. This is sort of a little bit shy of that. We're being a little fast and loose about, is this actually the probability or is this just the probability based on a limited sample? This is an estimate of the probability of each of these. There could have been some underlying principle that was like how many oranges I needed for a recipe, how many pears I needed. Like suppose every time I make my fruit smoothie I needed whatever, 1/10 of an apple, 3/10 of a pear, and 6/10 of an orange. And so I have only one piece of fruit equivalent in each smoothie, but it's weirdly distributed among these fruits, and so I might buy them in that proportion, right? So that would be my recipe would be the governing principle for the underlying probability distribution. The fact that I bought 10 fruits this time around, I might have bought 100, and I still would have expected the same likelihood for each one. So the sample, the sample might be small, and involve other random things. Like I might have had some apples at home, and so actually this particular shopping trip might not be indicative of the overall probabilities that represent the recipe. Does that make sense? So in the real world, during this thing, you've got like lots of randomness, you're taking small samples, lots of weird other things are happening. Maybe there is an underlying principle that decides the likelihood of different outcomes. That would be the true probability, but in any limited sense, you're just taking samples of that. So we're writing these expectation values based on this like we knew the real probability distribution, but maybe in principle, maybe you want to separate in your head between like the actual underlying probability of each of these things and the sampled estimate that you built from a histogram. Okay? And so we're actually going to talk in detail about like how uncertain this is based on the number of samples. That's one of the things we want to get to as we talk about statistics. That's a really important thing, is like when you form a statistic from a limited sample, how representative is that statistic? So in this particular bunch, I've got $2.50. If I grab 10 again, it might not be exactly $2.50, maybe it's $2.4 average. Are those actually different? Or are they just different sets of 10 things drawn from the underlying probability distribution with limited precision? So that's the kind of question we want to start thinking about asking. Does that make sense to everybody? All right, but so how do we, so we want to explain that spread, the bell curve thing, something like that. So what's another, how could we represent the fact that some of these are in this pile and only a few of them are in this pile, a lot are in that pile, given that we already know the mean? So if I took the mean, and the mean is 2.5, so I could have 10 fruits that all cost $2.50, but I don't. I have this weird other distribution. And we think we could move it around, so I could take one orange out, and then that would slightly lower my average. And I could put one, or let's say, I could add another orange, that would slightly raise it, and then I could add an apple to try and bring it back. So that, you know, like, just stick to 2.5 as the average. I could do that. Or I could have had 10 fruits that were all $2.5, and it would be a single spike for one value in the histogram. So how do I, what's something else I could do other than taking the sum of these things here? We take the standard deviation. So how is that different from the sum?
It shows variation about
It's the variation about the mean. So I could think of taking xi, my cost, subtracting off the mean of x. What's the average of this? This is the same, this is constant. So I can, well, I mean, is this a linear operation? Multiplying by probability and summing? Yes, so I could break that up into a sum from I equals 1 to 3 of hi xi over n minus the sum I equals 1 to 3 of average value of x, but that can come out since it's the same for every one, hi over n. This object is just the sum over all the probabilities, and we wrote down over there that the sum over all the probabilities is 1. So this whole thing goes to 1 times average value of x, and what's this? This is the average value of x from over there, right? So this is the average value of x minus the average value of x, so it's 0. So average this kind of distance away from the mean is 0. Because the mean already took care of that. So how do I stop that from being 0? I've got some things that are above and some things that are below.
You can do an absolute value.
I can do an absolute value, or I could do a square, or I could do a square root. I could do any other power that I want, and it wouldn't add up to be something. So the absolute value is a weird one, even though it's very tempting to do that. It turns out that the absolute value, because it has a kink in it right at the origin, is kind of badly behaved for propagating statistics through. So more commonly, we would do the mean square of the deviation. And then if we do the mean square, then this one comes out to be x squared. This one comes out to be this, and then there are a couple of, I'm not even gonna do that. There are a couple of funny cross terms that come out, but this thing is not equal to 0. In fact, it's equal to the standard deviation squared or the variance. Does that make sense, everybody? It's, in general, you might think about the average of lots of quantities. So this is the mean, and sometimes that's written with a sigma, with a mu. This is the second moment, which is related to the variance, but this guy, if we centralize this so that we take it as distribution away from this first one, and then we take the average of that, then that's sigma squared. This is the variance. Or we can take the third moment, or we can take the absolute value if we wanted to, even though it might get us into trouble. So in general, in our averaging formula, where we're saying the expectation value of x to the n is the sum of the probability I times xi to the nth power. And if I have so these are called the statistical moments of this probability distribution. So a probability distribution function is just the histogram after you take a lot of experiments and you are pretty sure that it's something you're converging toward. Okay? So this is a moment, and then this guy is the standard deviation. This guy is the variance. The standard deviation, or the root mean square deviation, has this funny thing. So why doesn't the square cancel out with the square root?
Because it's the average.
Because you average in the middle. Yeah.
What's the difference between that variance? Like the one on the right has the HI over N term.
Yes.
So
This one
versus that one.
and this one.
Whereas
These are the same.
Okay.
Oh. If you do this out and you say, oh, I'm going to multiply this times this, you have to be careful because there are they're cross terms, but the cross terms end up vanishing because of the same kind of arithmetic that we had down here where it was like the average minus the average before.
But what happens to the HI over N terms?
So these are the probabilities. These are these guys. So this is the same thing as I'm saying, don't take the cost of the apples, take the cost squared of the apples. Don't take the cost of the pears, take the $2 square it, $3 square it. That would be our second moment.
Okay.
And then this one is take not $1 for each, but $1 minus the average value of $2.50 would square it. So this would be negative $1.50 squared. Gives you this guy.
I think I'm still confused. I just don't know why you don't have the HI over
That's because he's
enter.
taking the average of.
Because I'm summing over all these.
Okay.
And
it's a
so,
different-
here, the easier one is this guy. So, sorry, in the last one, we did this, right? And so, HI over N times this, so there's one sum, HI XI over N minus sum HI average value of X over N. And then we went back over here and we said, oh, look,
I
Here's
saw
the-
that that one goes to 0, but you wrote xi minus the average value of x squared times the probability equals variance squared.
yes. Oh, did I just write something?
You had a square on that.
This one's squared.
Equals the variance squared.
Yes, that's sort of just definitional.
Okay.
But
I think I'm wasting time. I just-
no. Let's do this out. Let's see where it goes. It's gonna work. I'm confident it's gonna work, so let's see how it works. So this would be HI XI squared over N plus 2 HI XI average value of X over N
It's not a
minus plus average value of X squared HI over N. Is that right? So this one is this one. Right, just by this definition. This one is the X comes out minus 2 times this one squared. Because this guy comes out, and then I have the 2 comes out, and then I have HI XI over N. So I've got the same form as I had on this one, same form as over there. What about this one? The X squared comes out, then I have HI over N left. What's HI over N? Sums over. It is the probability individually, but if I sum over all the probabilities for all 3 stacks, what do I get? Just 1. So this guy becomes plus X squared. But this becomes this one minus this one. So you can do this variance 2 different ways, is what this little proof shows us. It could be that I take the mean away before I square it and average it. Or this is equal to this guy minus this guy. So I could either remove the mean at the beginning, or I could take the second moment minus the first moment squared. And both of these are equal to the variance. Does that make sense? So this is sort of like, this isn't wasting time, but this is totally like the kind of manipulations we want to get used to as we're moving these around. Does that make sense to everybody? So I can build all these moments, and from these moments I can build things like the variance, or the square root of the variance is called the standard deviation. Why would we care about the standard deviation rather than the variance? Think about the units. What are the units of variance here? mean is in dollars.
You said the 90s?
Yeah.
Dollars.
Yeah, which is kind of a weird thing. So like, knowing that the variance is like however many dollars squared, like $2 squared, doesn't mean much. But to say that the standard deviation is square root of $2 squared, $1.4, then we have all the kind of notation where we would say like, it's $2.5 plus or minus the standard deviation in dollars, whatever it is. I'm not going to go and calculate the standard deviation from this pile. But this gives you something in the same units as the mean, but it expresses the spread about the mean. So looking at these two, like, how do we make the spread bigger? Like, how do I increase the variance or increase the standard deviation?
Increase the number of points that are away from the mean.
Away from the mean. So if I pile them all at the mean, then the standard deviation of the variance would be 0. But if I put them far away, so if I manage to get $2.50 by putting most of them in this stack and then having just a few others, I would have a very small standard deviation, but I'd have the same mean. Or I could spread them way, way, way out. I could, for example, this is the if Jeff Bezos walks into the room, the average income, the average wealth of everyone in the room goes up by like $1 billion. That's not meaningful to us necessarily, but you might want to describe the spread as well as the average in order to reflect those kind of uncertainties, right? Does that make sense to everybody? Okay. So what about the third one? What's that oddball? This one has a special name, actually. Maybe you haven't seen it. Maybe you have seen it. This is the skewness. So one thing that this one doesn't tell you about is whether the spread is more towards the low end or more towards the high end. If you have, just distance squared, so it has no sense of the sign, so this is an even function. Hey, here's an odd function. The odd function tells us about the asymmetry about the mean. This one tells us about the spread about the mean. Does that make sense to everybody? And so we can go on to the fourth order one is called the kurtosis, et cetera, et cetera. All those things are things we can think about, and we will keep thinking about them, but this is the basic idea. We build these moments, and then we can use them to describe the underlying distribution. Yeah.
Just to clarify real quick, those are the average, not parentheses.
This is an average.
The one on the way outside.
This is an
Okay,
average.
cool.
This one is just a parentheses to make this cube work. Yeah, sorry. Okay, so this is the concept of moments. All right, what if I didn't have discrete bends, but I actually had a function that I was estimating? So now I'm going to let cost be a continuous variable. Can't use the sums anymore because we needed like discrete bins to count up these guys. But we can use this integral form. So in this case, this guy, which we had just written as a density, the same variable that we use for density when we were talking about mass, is also called the PDF. So in this case, PDF is the probability distribution function, and in this case, we call it the probability density function. And the way to interpret it is that the probability that x is between a and b is the integral from a to b of the probability density function. That makes sense to everybody? So this is a continuous generalization of the idea of a histogram. So when we're using a continuous function, measuring temperature, measuring distance, measuring things that are